Hello, everyone, and thank you for viewing this presentation. My name is Cindy Devlin, and I'm the DHEC Project Manager for the Bluewater Thermal Solutions site. I will be presenting the proposed plan for cleanup of the Bluewater site. In this presentation, I will explain what a proposed plan is and the purpose it serves, go through a brief history of site activities to date, discuss proposed cleanup alternatives, share DHEC's preferred cleanup alternative, and describe how you can share comments and questions with DHEC on the Bluewater proposed plan for site cleanup. DHEC has completed an evaluation of cleanup alternatives presented in the feasibility study for the Bluewater site. The proposed plan includes summaries of all cleanup alternatives that were evaluated and identifies DHEC's preferred alternative and the reason this alternative has been chosen. The purpose of the proposed plan is to inform the public of activities at the site, obtain public input on the cleanup alternative chosen, and fulfill the requirements of the Comprehensive Environmental Response, Compensation, and Liability Act, CERCLA, and the National Oil and Hazardous Substances Pollution Contingency Plan. The public comment period will run from July 25th, 2023 to September 25th, 2023. DHEC will select the final cleanup remedy after reviewing and considering all comments received. DHEC may modify the preferred alternative or select another response action based on new information or public comments made during the comment period. The public is encouraged to review the proposed plan and all documents available on DHEC's website for the Bluewater site. This is an aerial view of the Bluewater thermal site. The site is in the center of this figure, identified with a black outline. The site is located at 100 Hunts Bridge Road in Fountain Inn, South Carolina. It's located off Interstate 385 and south of State Road S3731, approximately 2 miles southeast of Fountain Inn, in a commercial and agricultural area. The site began operations in 1968 as Carolina Commercial Heat Treating, Inc. to process steel, stainless steel, cast iron, and other industrial materials. In 1996, Gibraltar Steel Corporation of New York acquired Carolina Commercial Heat Treating through a stock purchase agreement. Bluewater Thermal Processing, LLC, purchased a substantial amount of assets of Carolina Commercial Heat Treating and Gibraltar Steel, including the site. In 2012, Bodycoat purchased the site from Bluewater Thermal and currently operates the site. The main contaminants of concern found in soil and groundwater are tetrachloroethene, PCE, and trichloroethene, TCE. Other contaminants present at the site include 1,1-dichloroethane, 1,1-dichloroethene, toluene, chloromethane, chloroform, and cis-1,2-dichloroethane. From 2012 to 2018, various phases of environmental assessment were completed at the site to determine the extent of soil and groundwater contamination. In 2015, Gibraltar Industries and Bodycoat entered into a responsible party voluntary cleanup contract with DHEC. A remedial investigation was conducted from 2016 to 2018 to assess the extent of soil and groundwater contamination. The feasibility study and subsequent revisions were submitted in 2020. The main area of concern identified at the site is the area near groundwater monitoring well MW1S16, where groundwater contaminant concentrations were historically as high as 4,100 micrograms per liter for PCE. The Environmental Protection Agency maximum contaminant level is 5 micrograms for PCE. This figure shows the extent of PCE groundwater contamination at the site. Groundwater monitoring wells in the shallow aquifer are screened from approximately 20 to 30 feet below ground surface. The highest concentration of PCE is found at TW10 with a concentration of 680 micrograms per liter. The EPA maximum contaminant level for PCE is 5 micrograms per liter. The groundwater contaminant plume is contained on site. This figure shows the extent of TCE groundwater contamination at the site. The highest concentration of TCE is found at TW11 at a concentration of 20 micrograms per liter. We refer to our site cleanup goals as remedial action objectives. They are developed to set goals for protecting human health and the environment. The remedial action objectives for the site are to prevent leaching of contamination from soil to groundwater, remediate groundwater to prevent exposure to human receptors, and reduce the contaminant concentrations below federal and state maximum contaminant levels. Based on information collected during site investigations, a feasibility study was conducted to identify, develop, and evaluate cleanup options and remedial alternatives. The cleanup alternatives that have been evaluated as potential remedial alternatives are no action, institutional controls and monitored natural attenuation, in situ chemical oxidation, in situ enhanced biodegradation, and groundwater extraction, treatment, and discharge. I will provide a description for each of the cleanup alternatives and the costs associated to implement each remedy. Alternative 1, no action, is included as a baseline for comparison with other cleanup alternatives, which is a requirement of the National Contingency Plan. This action does not include institutional controls or groundwater monitoring. There is no cost associated with this alternative. Alternative 2 includes implementing institutional controls and monitored natural attenuation. MNA is a passive approach that monitors the natural degradation or reduction of contaminant concentrations in groundwater. Groundwater chemistry and contaminants of concern are monitored through groundwater analyses to continually evaluate and confirm that natural degradation is occurring. A groundwater monitoring program would be developed to evaluate remedy performance. Institutional controls include restrictions on land use, development, and groundwater use. The cost for this alternative is approximately $250,000. Alternative 3 includes injection of sodium persulfate and oxidant into the subsurface to react with contaminants of concern. Sodium persulfate injections would be completed over a grid pattern using direct push technology in the source area and hotspots. Groundwater monitoring would be conducted to assess remedy performance. The cost associated with this alternative is approximately $600,000. Alternative 4 combines in situ enhanced biodegradation with institutional controls. A dilute carbon substrate would be injected into the subsurface in up to 10 injection wells. The injections would be focused in areas containing elevated concentrations of contaminants. Injections would be performed once a year for approximately 3 years. Groundwater monitoring would be conducted to evaluate the effectiveness of the remedy. The cost for this alternative is approximately $650,000. Alternative 5 combines the use of groundwater extraction, treatment, and discharge. 3 extraction wells would be installed along the path of the groundwater contaminant plume. Contaminated groundwater would be pumped from the extraction wells to a treatment building containing an air stripper. Treated groundwater would be discharged to a publicly owned treatment works, POTW. Secondary treatment using a granular activated carbon unit, a GAC, may be required prior to discharge to the POTW. Groundwater monitoring would be conducted to evaluate the effectiveness of the remedy. The cost for this remedy is approximately $900,000. The National Contingency Plan requires that DHEC use specific criteria to evaluate and compare the different remediation alternatives to select a remedy. The evaluation criteria are overall protection of human health and the environment, compliance with state and federal regulations, long-term effectiveness and permanence, reduction of toxicity, mobility, or volume through treatment, short-term effectiveness, implementability, and cost. The final criterion we evaluate is community acceptance of the preferred remedy. This is evaluated after the public comment period has ended. Based on community acceptance, DHEC may modify the preferred alternative or select another remedy. The following slides summarize how each criterion is evaluated for each alternative included in the feasibility study. Overall protection of human health and the environment. When evaluating alternatives in terms of overall protection of human health and the environment, consideration is given to the manner in which site-related risks are eliminated, reduced, or controlled through treatment, engineering controls, or institutional controls. Alternative 1 does not provide control of exposure or reduction of risk to human health or the environment because no active remediation is employed. Alternative 2 is a passive approach that relies on natural processes to reduce contamination in groundwater, extending the remediation timeframe. Alternatives 3 through 5 employ active remedies that are expected to be protective of human health and the environment by reducing concentrations of contaminants in groundwater within varying timeframes. The in situ technology proposed in Alternative 3 has previously been used at the site in a pilot study, which resulted in a reduction in contamination. Compliance with state and federal regulations. This criteria evaluates whether an alternative meets federal and state environmental statutes and regulations that pertain to the site. Alternative 1 does not meet regulatory limits because no active remediation is employed to remove contamination. Alternative 2 is a passive remedy, so it may meet regulatory limits over an extended time frame. Alternatives 3 through 5 would meet regulatory limits within varying timeframes. Alternatives 3 and 4 rank higher because in situ treatment targets reduction in the source area. Long-term effectiveness and permanence. This criteria looks at how effective the alternative is at reducing the risk at the site and the reliability for the remedy to maintain a reduced risk over time. Alternatives 1 and 2 are the least effective long-term because these remedies do not involve active remediation. Therefore, extending the length of time groundwater contamination remains. Alternatives 3 and 4 address source area contamination through oxidation and biodegradation using in situ technologies. Alternative 5 includes extraction, treatment, and discharge of contaminated groundwater. The source of contamination is not directly addressed with this remedy. Reduction of toxicity, mobility, or volume through treatment. This criteria is the degree to which an alternative employs treatment to reduce the harmful effects of contaminants, limit the ability for contaminants to move in the environment, and how the alternative reduces the amount of contamination present. Alternative 1 does not employ any treatment to reduce toxicity, mobility, or volume of contamination. Alternative 2 may reduce toxicity or volume, but would take an extended time frame to accomplish remedial goals. Alternatives 3 and 4 reduce toxicity and mobility of contamination using in situ techniques that target the areas of highest contamination. Alternative 5 reduces mobility and volume of contamination using groundwater extraction and hydraulic control, but does not directly address the source of contamination. Short-term effectiveness. This criteria considers any risk the alternative poses to on-site workers, the surrounding community, or the environment during implementation, as well as the length of time needed to implement the alternative. Alternatives 1 and 2 do not involve active remediation, therefore no short-term risks exist to the community, workers, or the environment. Alternatives 3 and 4 use in situ technologies to treat groundwater contamination. Materials used during installation are injected in place without having to excavate soil or pump groundwater for above ground cleanup. Alternative 5 includes the installation of extraction wells and operation of an air stripper. Operation of the air stripper could exhaust vapors to the atmosphere. Implementability. This criteria considers the technical and administrative feasibility of remedy implementation, as well as the availability of required materials and services to complete the alternative. Alternatives 1 and 2 do not involve construction, operation, or maintenance of a remedial system, so there is no issue with implementation. Alternatives 2 through 5 require injection of amendments, groundwater extraction, and treatment, all of which have been successfully used to remediate similar sites and similar geologic settings. These services are commonly implemented, and there are ample experienced contractors to perform these services. This table ranks the alternatives from 1 to 6 based off their effectiveness in each criterion category. The scoring system gives each alternative a ranking from very favorable with a score of 6 to very poor with a score of 1. As you can see from the scoring system, alternatives 1 and 2 score the lowest because while they are easy to implement, they do not provide human health and environmental protection, meet regulatory standards, or provide long and short-term effectiveness. Alternatives 3 through 5 score better because they include active remediation to address several criteria. The scores for alternatives 3 and 4 are the highest. Alternative 3 is preferred because a pilot study previously performed at the site using in situ chemical oxidation resulted in a reduction in contamination. DHEC has identified alternative 3, in situ chemical oxidation, as the preferred remedy for the Bluewater thermal site. Sodium persulfate, a chemical oxidant solution, will be injected into 8 injection points within the groundwater plume. The injections will be completed using direct push technology to permeate the areas of contamination. In January of 2019, a pilot study was performed at the site using in situ chemical oxidation, confirming that this alternative will be successful at remediation of contamination. Routine groundwater monitoring will be conducted to evaluate remedy effectiveness. Institutional controls will also be implemented. The total estimated cost is $600,000. This figure shows the treatment area for the preferred alternative, alternative 3, in situ chemical oxidation. The small black circles dashed in the yellow dashed area represent the locations for the sodium persulfate injections. This alternative is the best solution in terms of overall protection of human health and the environment, long-term effectiveness and permanence, and reduction of toxicity, mobility, or volume through treatment. The next steps in the process involve DHEC accepting all comments or questions on the proposed plan until September 25th, 2023. After DHEC reviews all public comments, DHEC will identify the selected remedy in a recorded decision. Following the recorded decision, DHEC will work with the responsible parties to develop a plan to construct and implement the selected remedy. DHEC has created an administrative record that includes the proposed plan and all supporting documents for the proposed plan. DHEC's administrative record can be found on DHEC's webpage, www.scdhec.gov/Bluewater thermal. A copy of the administrative record can also be found at the Fountain Inn Library located at 311 North Main Street, Fountain Inn, South Carolina. DHEC encourages the public to review these documents to gain an understanding of the site and the activities that have been completed. DHEC will accept public comments on the proposed plan beginning today. Comments can be made in writing or by email to Cindy Devlin at 2600 Bull Street or at devlincl@dhec.sc.gov. If you have any questions about the site or the proposed plan, please contact me by email or at 803-898-0816. Once again, the public comment period begins today and is open until September 25th, 2023. Thank you for viewing this presentation.